Today, I would simply like to give you a few little ideas to put a bit of the immensity of the universe into your minds. An immensity that we will fly over in several stages, each of which may blow your mind in its own way. That being said, let's begin our journey toward immensity with something obvious. The universe is much bigger than we can possibly imagine. That's why, when faced with the enormous, extraordinary distances that separate us from other celestial bodies, we usually convert these distances into light time. In the void between the stars, a grain of light travels at the fastest speed possible in the universe and covers about 300,000 kilometers per second. To try to grasp this truly astronomical speed, just think that in the time it takes to blink once, a grain of light travels through space a distance equal to the circumference of the Earth. Let's pause for a second or so on this idea, and just like that, it has traveled from the Earth to the Moon. The time it takes for it to cover the roughly 384,000 kilometers that separate us from it. If we imagine that it were possible to reach our satellite by driving at 130 kilometers per hour on a hypothetical highway, it would take 4 months of non-stop driving to cover that distance. This image, to scale, shows the distance separating us from our satellite. At the speed of a standard airliner, it would take 18 days to cross it. The modules from the Apollo missions, which were speeding along at an average speed of 5,300 kilometers per hour, took nearly 4 days to make the journey and cross the immense distance that separates our planet from its satellite, and inside of which you could easily fit all the planets of the solar system or even 30 Earths. In short, the Moon is far away, and yet this positively immense distance is nothing compared to the space that separates us from the Sun. Because our star is approximately 400 times farther from us than the Moon is. Traveling through space at the average speed of 5,300 kilometers per hour that the Apollo mission modules had, it would take 3 years to reach the Sun. At the speed of a standard airliner, it would take 19 years to make the journey. And assuming it was possible to get there by car, taking a still hypothetical and absurd highway through space, well, you would have died of old age before arriving. Because by driving non-stop at 130 kilometers per hour, it would take you about 130 years to reach the Sun. And yet, our Sun is absolutely immense compared to the size of our planet, but also extremely small when you look at the dimensions of certain stars. Consider that the red giant Arcturus is nearly 25 times larger, Aldebaran is 45 times larger, and the blue giant Rigel is 78 times larger. And Rigel is itself a dwarf if you compare it to Antares, a red hypergiant nearly 900 times larger than our Sun, which would engulf the orbits of Mercury, Venus, and our planet if it were placed at the center of our system. And Antares is itself nearly twice as small as Iscuti, one of the largest stars in the known universe. If you placed Iscuti at the center of our solar system, Jupiter, even though it is 778 million kilometers away from our Sun, would end up inside the star. Yet, Iscuti, as giant as it is still tiny compared to the immense size of our solar system. To try to grasp the enormity of it, let's take a few seconds to look at a probe. Here is the object made by human hands that is the farthest from our world. Launched in 1977, the Voyager 1 probe is speeding through space at about 62,000 kilometers per hour. And after 48 years of travel, it has moved 160 times faster than a Formula 1 car. It is only about 6 times farther from the Sun than Neptune. In 2012, Voyager 1 crossed the boundary of the heliosphere, the bubble created by the solar wind, and has been traveling through interstellar space ever since. Today, at a distance of about 25 billion kilometers from our star, this probe still hasn't even traveled a single light day since it was launched. That distance will not be reached until February 2027, and above all, Voyager 1 is still very, very far from leaving the solar system. It is estimated that it will take nearly 2,500 years before it begins to enter the gigantic, evenly distributed cloud of debris that surrounds the Sun on a large scale, and about 25,000 years before it leaves it and finally crosses the gravitational boundary of the solar system. By then, the probe will have traveled just a quarter of the distance between us and the nearest star. Voyager 1 did not head toward that small red star called Proxima Centauri, but if it did, it would take nearly 100,000 years to get there and cover the 4 light years that separate us from it. To fully convince ourselves, to realize that the space around us is vast, let's go back for a moment to the size of our solar system. Here you have to scale the orbits of the 4 inner planets of our solar system, as well as that of the gas giant Jupiter. In this image, the Sun is obviously not to scale, because in this reduced representation, it is actually smaller than an atom. And now here are all the elements from the previous image compared to the orbits of the gas giants, and to the position of the dwarf planet Sedna. This body has an extremely wide eccentric orbit. It is currently half a light day away from the Sun. But Sedna's orbit is so vast that it takes this dwarf planet about 11,500 Earth years to complete 1 revolution around our star. At its farthest point, Sedna is at a distance nearly 1,000 times greater than that which separates the Earth from the Sun. And yet, as gigantic as it is, Sedna's orbit is insignificant when compared to the vast dimensions that surround the Sun. To try to grasp the staggering size of this cloud, as well as our solar system, all you have to do is follow the journey of a single particle of light that has just left the surface of the Sun. For this particle, traveling at the astonishing speed of nearly 300,000 km per second, it takes just over 3 minutes to reach Mercury's orbit, 6 to pass Venus's orbit, and about 8 minutes and 20 seconds to cover the 150 million kilometers that separate our star from the orbit of our planet. 12 minutes and 30 seconds after its departure, our photon reaches Mars's orbit, after which it still has to travel for another half hour to reach Jupiter's orbit. Then, 1 hour and 20 minutes after leaving our star, our photon passes Saturn's orbit. 2 hours and 40 minutes after leaving the Sun, it reaches Uranus. And nearly 2 hours later, our particle crosses Neptune's orbit and enters the Kuiper belt, a disk rich with hundreds of millions of comets and asteroids, through which it will speed for 3.5 hours before leaving it. After that, 2 weeks of travel through a void as immense as it is staggering are still needed for our particle of light to reach the inner edges of the vast Oort cloud, where it will travel for nearly an entire year, at the maximum speed possible in the universe before leaving it, and finally cross the gravitational boundary of our star, which marks the true limits of the solar system. Then, nearly 3 more years of travel are still needed for our particle of light to reach Proxima Centauri, the closest star to the Sun. A star that isn't even visible to the naked eye in the sky. It's important to understand that space is so vast that, with the staggering distances to cross, apparent brightness fades away like snow in the sun as the grains of light spread out in space. And only the most powerful stars can be seen from a great distance. So, the small red dwarf Proxima Centauri, even though it is 10 times larger than our world, while being located only 4.2 light years from the Sun, which is very close on the scale of space, literally right next door, is invisible to the naked eye from Earth and was only discovered using telescopes in 1915. And this astonishing dilution of light doesn't just affect small red stars. Imagine that a hypothetical observer located 50 light years away from us, with vision roughly identical to ours, wouldn't even see our Sun. So, out of the 6,000 stars that can be seen with the naked eye on beautiful clear nights, only 133 are located less than 50 light years away from us, while we have been able to detect 1,800 of them, all smaller and much less luminous than our Sun, using our telescopes. And now, these vast spaces that are beyond us begin to overwhelm us when we realize that almost all of the stars we can see with our own eyes in the sky fit inside this small sphere. What you have here is the volume of space around us in which almost all the stars you can see with the naked eye are located. When you look up at the sky, you are only seeing a tiny part of infinity because this sphere with a diameter of 1,000 light-years is just a tiny portion of our galaxy, the Milky Way. A vast collection of clouds of gas, dust, and stars, nearly 100,000 light-years wide and 1,500 light-years thick. To try to grasp all this immensity, keep in mind that all the images we show you of our galaxy are and will forever remain digital representations, reconstructions made from data collected from inside, from where we are, in the second spiral arm, 25,000 light-years from the center. To reach a point far enough away to take a picture capturing our entire Milky Way, it would take about 550 million years at the speed of the Voyager 1 probe. Despite everything, from Earth, our eyes, like our telescopes, give us a splendid glimpse of the roughly 300 billion stars and planetary systems that our galaxy contains, and that we can observe as a Milky Band stretching across the sky from one end to the other. The Milky Way is therefore absolutely gigantic, and I choose my words carefully. In fact, it is so vast that its size remains absolutely staggering, even when we simply imagine shrinking all its components to astonishing proportions. Let's imagine that all the objects that make up our Milky Way are 70 billion times smaller than they are today. In this reduced universe, our star is the size of a sphere with a diameter of 2 seminatros. And 2 meters away from this tiny sun is our planet Earth, which at this scale is about the size of a pinhead. Jupiter, the largest planet in the system, is the size of a lentil and orbits 8 meters farther away. Meanwhile, Neptune is the size of a grain of semolina drifting 67 meters away from our tiny sun. In this little game, the Voyager 1 probe is hardly bigger than an atom located 280 meters away. Proxima Centauri, the closest star, is 580 kilometers away from our shrunken sun. And the center of our Milky Way is 3,700,000 kilometers away, which is 10 times farther than the moon is from us in the real world. And if we keep shrinking the size of all the elements in our galaxy to the point where our sun is the size of a small lentil, even then, the Milky Way still stretches over twice the distance that separates the Earth from the moon in reality. In fact, the Milky Way is so big that even if you shrank our sun down to the size of a white blood cell, then proportionally our galaxy would be as vast as Europe. "150 years ago, the Milky Way was the only galaxy in the known universe. Today, we have trouble even estimating their number. In the universe, we find them everywhere, no matter which direction we look. In 2003, astronomers pointed the Hubble Space Telescope at an extremely dark and tiny corner of the sky. To the naked eye, its apparent size is equivalent to the surface of a pinhead held at arm's length. And after 1,000,000 seconds of exposure time, they got this. One of the most extraordinary photos ever taken by humans. A small number of the bright spots you see there are nearby stars in the foreground, but the rest, absolutely everything else, is just galaxies. In this single photo, by carefully analyzing all the data, nearly 10,000 have been identified. And this photograph is just a tiny fragment, an infinitesimal portion of the sky that you see here next to the moon. It would take about 23 million photos like this one to cover the entire night sky. So, it is estimated that the number of galaxies in the observable universe is about 2 trillion. Let's take a look at one of the closest to us, the Andromeda Galaxy. It's twice as large and contains 3 times more stars than our Milky Way. This spiral galaxy is so vast that it would cover an area of the sky nearly 5 times larger than the full moon if it were just a bit brighter, as shown in this image. Andromeda is currently 2.5 million light-years away from us. This means that the light reaching us today left the stars of this galaxy at the time when Homo habilis was still roaming the plains of Africa, more than 2 million years before the appearance of the first Homo sapiens. Even though it is 2.5 million light-years away in cosmic terms, Andromeda is literally the next-door neighbor. And yet, this galactic neighbor will probably remain forever out of reach for us. Consider that to cover the distance that separates us from it today, the Voyager 1 probe would take 56 billion years, a span of time nearly 4 times longer than the age of the universe. So, in the universe, when we talk about close neighbors, you really have to put a lot of space between the quotation marks.
Andromède comme notre galaxie.
The Milky Way are both part of what we call our local cluster, a group of about 50 other galaxies gravitationally bound together. And this local cluster itself is only a small part of what we call our local group. A large group 10 million light-years in diameter and containing more than 1,000 galaxies. And this local group is in turn a subset of a colossal structure, the Virgo supercluster, whose staggering size, millions of light-years in diameter, and which contains about 10,000 galaxies spread across 100 different clusters. And this Virgo supercluster is itself contained within an even larger structure, since it's estimated that there are several million such structures in the universe. Everywhere we look into the deep sky in all directions, we observe superclusters of galaxies that, on the largest scales, take the shape of an immense cosmic web, stretching over tens of billions around us, and which would contain, as we've said, about 2 trillion galaxies combined. But everything we've just covered is only the part of the universe whose light has had time to reach us since the universe began. And that's what we call the observable universe, which is surely only a tiny portion of the total universe. So, even though the overwhelming geography of the known universe ends visually, at a horizon currently located 45 billion light-years from us, there are very likely billions of other superclusters of galaxies beyond the limits of our sight. So it's likely that the immensity we can observe today with our telescopes, which is already incredibly difficult to comprehend, is itself ridiculously small compared to the size of the universe as a whole. It's even possible that it never ends, that the universe is infinite, and that the dimensions of what lies beyond are themselves beyond anything the imagination of humans who appeared on this planet, here, in this galaxy, is capable of conceiving. To try to grasp the immensity of our observable universe, we can have some fun by reducing its dimensions so that our galaxy's real 100,000 light-year width fits within a diameter of 1 meter. In this miniaturized universe, where the Milky Way is transformed into a luminous disk 1.5 centimeters thick, which can fit between your outstretched arms, the Sun is just a microscopic speck of dust located 2/3 of the way from the edge of the disk. And almost all the stars visible to the naked eye are found in a region less than a centimeter wide around that tiny speck. 25 meters away, in the darkness of the surrounding space, lies the Andromeda Galaxy, which is 2 meters wide. Bound by gravity to about 50 other smaller galaxies, the Milky Way and Andromeda together form our local group. A vast coherent structure that, on this scale, stretches about 100 meters wide. In the distance, the Virgo supercluster, which contains nearly 10,000 galaxies, sprawls across a structure more than 1 kilometer across. And everywhere, in all directions, thousands of superclusters like this can be seen, all the way to the edge of the observable universe, which is nearly 460 kilometers from our 1 meter wide luminous disk. A distance that is roughly the same as the one between Paris and Bordeaux. In short, to sum up all this immensity in just a few words, space is big. And to finally wrap up this story, let's have some fun this time by fitting the distance separating us from the edges of the observable universe into a series of books with black pages. Imagine that the Sun is reduced to the size of a small 2 cm sphere printed on the cover of a collection of 250-page books. In this little game, the planet Mercury is on page 4, Venus on page 8, Earth on page 10, Mars on page 16. Jupiter is on page 55, Saturn is on page 100, Uranus is on page 200, and Neptune, the last of the gas giants in our solar system,
perdu dans l'immensité noire,
on the 75th page of the second book. The Voyager 1 probe is at the beginning of Volume 7, and the outer limits of the solar system appear around the 3600th book. As for the star closest to the Sun, it is around the 11,000th book. To fit the distance separating us from the edges of the Andromeda Galaxy into these books, it would be necessary to print 6.5 billion volumes. Such a quantity of books would require a space 300 times larger than that of the largest library in the world to be stored. What if you take the thought experiment further and try to cover the distance to the edge of the observable universe? In this reduced printed universe, you would need to cover an area as large as France. With 12-story buildings packed to the brim with books almost entirely black with ink, mirroring the emptiness of space, only occasionally disturbed by the presence of rare stars. And if, after all that, you still haven't managed to grasp even a bit of the insane size of the universe, shrunk in your minds and feeling small and crushed in the face of the immensity of the universe, just remember that you are actually a giant much bigger than you think. Because even though the Sun is immense compared to the size of our planet, proportionally speaking, you are nearly 10 times bigger to a water molecule than the Sun is to you. And maybe that's the craziest part of this story. At the infinitesimal scale, the distances that, proportionally speaking, separate the components of matter are even more staggering than those in the vastness of space. In fact, the difference in scale between the size of a proton and the smallest unit we suspect exists, called the Planck length, is the same as the difference between the size of a human being and our galaxy. For example, a pollen grain compared to 1 light year. In fact, the Planck length is so small that, proportionally speaking, we are 10,000 times closer in size to the largest thing we can see, that is, the observable universe, than to the smallest thing we suspect exists. And that's really incredible. To dive into the dizzying vastness, I recently released Voyages dans l'infiniment grand, a comic book that takes you on a journey to explore the immensity of the universe, and you can find it at all good bookstores.